All right, so we want to talk a little bit more about coordination compounds, specifically their bonding. So let's do a little review. I have methane here, sodium chloride, and then I have this coordination complex with scandium complex with water molecule ligands. So recall methane is a covalent compound, right? Each of these carbons covalently bond with hydrogen. Sodium chloride is an ionic compound. And with covalent compounds, we have this sharing of electrons. This sharing of electrons, which is why it's such a stable interaction. So each carbon-hydrogen bond involves an electron from carbon and from hydrogen. They're doing a sharing. Sodium chloride, right, ionic compounds, involves electron transfer, Now remember, with coordination compounds, we form what's called a coordinate covalent bond, where the Lewis base donates an electron pair, both electrons, to the Lewis acid. So in this example, our water molecules behave as a Lewis base, and each of them donate an electron pair to the Lewis acid, which is this metal ion scandium. So just doing a little comparison here of the different types of bonding that we have. So just summarizing what I just said: covalent bonds, electron sharing; ionic bonds, electron transfer; coordinate covalent bonds, electron donation from a Lewis base to a Lewis acid. So in coordination compounds, transition metals usually can make up coordination compounds, or we might use the term complex ions or a coordination complex. And transition metals behave as the Lewis acid, so they receive or accept the electron pair from whatever ligands they are bound to. So here is a general formula for coordination compounds, where M stands for metal, Lg ligand, the overall charge of the coordination complex, and then A is our counter ion. So usually the metal is this central atom that behaves as a Lewis acid, and each of the ligands that's coordinated to that metal behaves as the Lewis base. And if we sum all of the charge of the metal, transition metal ion, and the ligands, we get the overall charge. So the counter ions, which is not always present, it depends, right? The counter ion is, if you think about it intuitively, right, it's countering the charge on the coordination complex. So it balances out this charge. So that's the whole point of a counter ion, to balance out the charge of the coordination complex. Now, what's called the coordination sphere is the central atom coordinating the ligands. And the counter ion exists outside of the coordination sphere. So coordination number. This number is the number of donor atoms or Lewis bases that are bound to the central atom. So we're talking about the coordination sphere. The coordination sphere tells us the coordination number. So first example, we have silver as our central atom, central metal, and it is coordinating two ligands of ammonia. So it has a coordination number of 2 because there's 2 ligands bound. Another example, we have copper coordinating 4 ligands of chloride ions, so its coordination is 4. And our last example here, we have cobalt that's coordinating 6 different water molecule ligands, so its coordination number is 6. So coordination number, number of ligands or Lewis bases that are coordinating or bound to our transition metal central atom.